We're going to start. Good afternoon, everybody. Thank you so much for people attending online, people here. For people attending online, we have about 100 people in the room. It's packed. Okay. We welcome you all to John Brackins' PhD defense. Um, so this is going to be a long talk in a good way. Okay, you're going to learn a lot of new things. What I want to say is first we'll go over a public presentation where John will present his dissertation, his progress, and the floor will be open for questions from general public. After which we will ask that the general public excuse us. So the committee will have a one-on-one discussion with John, and that concludes the whole dissertation defense process. Before we start, though, I do want to say a few things about John. I was just reflecting over yesterday, and I did not realize, John, it's been 8 years. It feels like it went just like that.
I agree.
I've known John for 8 or more than 8 years, and back when he was a sophomore, and I realized at that point there was this student in the department office who was always doing something. That's what I got, and learning something. And he was so interested in learning that he actually read the Tennessee law. I think I forget the name of that. I'm sure
Tennessee Code Annotated.
There you go. There you go. So that got me. That was very interesting for me. And thankfully, I have to thank Miss Anisa Milam and Don Taylor. I was looking for students who can help me with research at that time. And sure enough, John was available. And John was not really convinced with the whole water resources and environmental engineering thing. But thankfully, it took about a research project and few presentations to actually get him motivated. And slowly, I was able to encourage him to explore the research area of water resources engineering. And he's been focused ever since on flooding. Specifically, he's been focused on coastal flooding. And that's what got him through his undergraduate. From a research standpoint, that he went through his undergraduate, and then he decided to stay at Tennessee Tech, did his master's, and now the culmination is basically going to present his dissertation. And I have to say, though, John is one of the only two students who are in our department who have ever received the prestigious National Science Foundation Graduate Fellowship, which is not easy. And I can tell you that it's been quite an accomplishment. Well, I don't know if you can realize I'm very well. Typically, I tend not to say in front of the students, but I have to say I'm very proud of you, John, for what I've seen you and how I've seen you grow as an undergraduate student to an independent researcher right now. And with that, I would like to leave the floor open to John so that he can present his dissertation. Go ahead.
Thank you, Dr. K. All righty. Do a little bit of setup here, make sure that everything's working. Everyone can see the slides. So. Can someone online please verify they can see the slides for us, please?
Yes.
You can. That works. All right, I'm going to minimize that so we can see everything. We'll be using most of the slide area available today, so there will be plenty of information. But thank you for that introduction, Dr. K. So just because we have to give this title out, I know everyone here can hopefully read it, but the title of the dissertation we'll be considering today is the evaluation of nonlinear interactions between tropical cyclone storm surge and rainfall runoff to improve understanding of joint coastal flood risk. So with that, let's begin. So the outline of the presentation, we'll go through the introduction and literature review, the research objectives that leads to, the methodology split into 3 objectives of how we decided to handle those objectives, the results for each of those, some conclusions, and then some final material and acknowledgements and time for questions for the general public. So let's get right into the introduction and literature review. So tropical cyclones, as we said in the title, a lot of people know them by their name: hurricanes, typhoons. We've lost the slides in the room. All right, slides are back up on Teams as well. Minimize that. All righty. Thank you for bearing with us. So let me just start fresh there. So we're looking at tropical cyclone, storm surge, and rainfall runoff flooding today. So looking at tropical cyclones, you might know them by the names hurricanes, typhoons. We're talking about tropical cyclones. So those names tend to refer to stronger storms of the same nature. I'm going to talk about tropical cyclones, which may involve weaker storms as well. So just wanted there to not be any confusion with that. Essentially, they're a meteorological disturbance that acts as a heat engine where warm, moist ocean air rising and forming thunderstorms over the ocean. The latent heat from that condensation fuels the tropical cyclone. And as those intensity builds and winds begin to swirl, the system rotates and organizes. So we have 4 stages of that very briefly. Talking about those weaker storms, we have a tropical disturbance that's just barely organized convection. It's non-frontal, maintains its identity for 24 hours. That's how transient they are. Tropical depression is a closed circulation now of a tropical disturbance. And then the tropical storm has become more organized, more severe, and eventually at a hurricane is where the winds exceed 74 miles an hour or 33 meters per second. So why do we as engineers care about tropical cyclones? Over the 40-year period, 1980 to 2019, 6 of the 20 deadliest natural disasters in the United States were tropical cyclones. So we have these grim statistics from names that we all recognize from the news. Maria, Katrina, Sandy, Rita, Ike, and Irma. And all of these storms and several others have caused a lot of damage as well. 14 of the 20 costliest U.S. natural disasters over the same 40-year period have been tropical cyclones, for a total of $775 billion in damages. So the flooding in coastal watersheds actually has 2 causes from tropical cyclones. There's the inland cause that we in Tennessee are more used to dealing with, the rainfall-runoff flooding from rivers and urban drainage. And then there's the shoreline causes, coastal flooding, which includes the effects of storm surge, waves, and tides. So why does it matter? Again, about 50 people per year still die in the U.S. from these disasters. And while our entire scale for hurricanes is built around the wind, category 1, 2, 3, 4, and 5 is built around wind, people worry about wind and they get hit by the water. 90% of fatalities are actually due to water, not wind, in these tropical cyclones in the United States. So where are the areas that we're talking about? What areas do you need to worry about? So we looked at the coastal watershed counties of the United States. And in the eastern seaboard there, we have the Atlantic that we would kind of suspect. We said North Atlantic hurricane season. The Great Lakes was an area that before I started this, I really hadn't suspected that. The lakes are large enough and deep enough that you can have storm surge generated, albeit it's smaller than you might see on an open coastline, but it can happen. Thankfully, the West Coast doesn't have to worry about it as much, but they have plenty of other things that they have going on. These coastal watershed counties are less than 20% by land area, but they're home to 52% of the U.S. population. So let's start looking at some of the physics behind these causes of flooding. So storm surge is driven mostly by wind, and it's also affected by decreased atmospheric pressure, the Coriolis force, bottom stress and friction, lateral stress, tidal potential, baroclinic pressure, stratification, and it's governed by the continuity and momentum equations, which you can combine together in the generalized wave continuity equation. So for those who may not have had differential equations in a while and would prefer a picture, here's the version of that. Essentially, we have a hurricane that's moving on land, and its wind is causing this water to progress towards the shoreline and has nowhere to go but up, essentially. And so that's what's generating storm surge in layman's terms. Some potent examples of that from history is the 1900 Galveston hurricane. There was a storm surge on Galveston Island to 20 feet above mean sea level. Well, at that time, the island itself was only 5 feet above mean sea level. And so that's 15 feet of inundation over the entire island in a time when communication was very poor, and trying to evacuate that many people off of an island just was not possible. So unfortunately, in that event, there were 6,000 people that were killed and 20,000 homeless overnight. It remains to this day the deadliest natural disaster in American history. We also had 1965 Hurricane Betsy, storm surge in New Orleans. It's the first hurricane to cause over $1 billion in damages. And then we have the one that everybody remembers. I remember watching it on the news when I was a kid, 2005 Hurricane Katrina with a storm surge of nearly 28 feet in Mississippi. The city of New Orleans, although there was an additional hurricane that dumped more rain in the process, was not free of floodwaters until 43 days later. It was the largest single loss event in the history of the global insurance industry at the time. Then let's also look at rainfall runoff. It's driven by pressure, gravity, the Coriolis force again, viscous effects, and bottom friction. It's governed by the shallow water equations, which these equations look an awful lot like the storm surge equations that we looked at briefly. Interestingly enough, storm surge is also a shallow water wave because it is such a long wave, even in the depths of the ocean, it can still be modeled using the shallow water equations. So we learned excess runoff leads to flooding. I was talking with Miss Donna beforehand, and she said, "What's your presentation about? Flooding? Oh, it's where there's too much water, right? Excess runoff leads to flooding." We all have a concept of that. So we have some examples here from 1999 Hurricane Floyd. The top is in North Carolina and the bottom in Virginia there. So some examples of what we're up against even on the rainfall runoff side. But that's not the whole story. These phenomena can interact because they're occurring on the same timescales. They're being driven by the same storm. So some examples where they have interacted in the past. 2017 Hurricane Irma in Florida, where there was significant urban flooding due to a combination of heavy rainfall up to 12 inches in 48 hours, and then the runoff from that failing to drain into the bay due to storm surge elevated water levels that were 4 to 6 feet above normal. 1998 Hurricane Zores in Puerto Rico, they had very small steep coastal watersheds, and so that's an area where this is important to look at as well. But you also don't even need a hurricane. You can have just a tropical storm. As we saw in 2008 Tropical Storm Faye in Florida, its slow forward speed of 3 to 4 knots, 1.5 to 2.1 meters per second, allowed very heavy rain to propagate over the same areas again and again for several hours. And so the watershed rainfall runoff from that added more than 1.5 feet to the storm tide elevation in the river and increased the flooded area by more than or by nearly 50%. You say 1.5 feet, 50%, there's a disconnect there. Look at, this is Florida that we're talking about. So 1.5 feet vertically is a very large area horizontally with flooding. So we said, okay, how can we as engineers deal with this? How can we get a picture of where these floods are going to happen ahead of time and build around that as best we can? Or if there are buildings there already, how can we plan for that? And so the Federal Emergency Management Agency has put together flood risk maps for many years. So this is an example in a coastal area of what we're looking at. So essentially just saying zone VE, I know this is tiny, tiny text, I can't read it and I put it up there. So that is looking at areas where waves are important for coastal flooding when you have a hurricane or a tropical cyclone coming in here. And then you have zone AE, which is the standard zone that's used for inland flooding purposes. It doesn't have waves riding on top of it that are greater than 3 feet. So just to kind of show that graphically as well, we have those V zones, you know, with the waves where you're closer to the sea, and then A zones that are coastal where you're further back, but you know, you may still have some waves, but not up to 3 feet. And then you have the inland area of the person who I would say more wisely built their house there. So how did we establish all of these flood risks? We have to come up with data from somewhere. Fortunately, these tropical cyclones are actually very rare events. And so we can't just look at it and say, what is the worst storm on record done and build to that, right? Because there can always be a worse storm. It can always be in a more critical track, a more devastating location than it was before. One classic example of that is looking at 2005 Katrina, 1969 Hurricane Camille, followed a very similar track, was a Category 5 all the way up to landfall. And everybody said, oh, we'll be dry in Katrina because we were dry in Camille. Well, what they didn't know was that Katrina was 2.5 times larger than Camille was and caused 28 feet of storm surge instead of 12. And so there's a lot of different factors. It's not just the intensity that we have to look into. So we need a way to consider all of these together. And so we looked at a joint probability method where we can characterize these storms by a small set of parameters that are either statistically independent or have some sort of known dependence that relationship that we look at, looking at correlation of these variables and doing a dependence relationship if necessary. So then we can look at the probability of a given storm and its flooding by the joint probability of the multiple parameters. We're going to look at intensity, storm size, forward speed, landfall location, and landfall approach angle. course, we want to do this over time. We want to say, how often do we expect this to happen? Is this the 1% annual chance event? Is this the 0.2% annual chance event, the 100-year and 500-year floods, so-called, respectively? And so we also need an annual rate of occurrence for that. Also, when we are simulating these, we have limited compute power. We can't just simulate this entire integral with a very large amount of realizations of each of these parameters. We need to step back and say, which are the storms that are most important for us to capture that get the best picture of the risk while limiting the computational resources that are necessary. So optimal sampling methods, JPMOS, allow an order of magnitude fewer combinations. There have been studies in literature that have shown that they can achieve that with a slight accuracy trade-off. Mean surge difference is actually near 0 feet, but adding about a standard deviation of about a half a foot to their overall uncertainty in exchange for the compute resources. So just as an example of that, looking at the different values that we might have for this is from 1981 in North Carolina. So they had several different values for central pressure depression, 2 different storm sizes, 3 different forward speeds. And so these were all assigned different probabilities. You would multiply the probabilities of particular combinations together to achieve the probability that we expect that storm in particular to occur based on climatology. So with all of that background, let's move into the research objective of where we are trying to add to the body of knowledge. So the overall main objective, we talked about storm surge, we talked about rainfall runoff and their interactions. The main objective is to develop a methodology accounting for the nonlinear interactions between storm surge and tropical cyclone rainfall runoff flooding. So we broke that into 3 sub-objectives so that they were more manageable. So objective 1, if we're going to look at rainfall runoff, we need to know the precipitation that is generated by these storms. Unfortunately, we're characterizing those storms by only 5 parameters. And so we needed some way to have parametric tropical cyclone rainfall models that are capable of providing those rainfall boundary conditions to a combined modeling system. And we hypothesized originally that tropical cyclone rainfall could be adequately represented for the purposes of coastal flood risk assessment using these parametric models that only take storm track information that we typically have. And so we compared that against observed rainfall fields. Second objective, we set out to create a coupled storm surge rainfall runoff modeling system. And again, hypothesized that hydrology models and hydrodynamic storm surge and wave models can be coupled together to adequately simulate joint flooding during tropical cyclone events, and looked at validation of that system insofar as we could. And the third objective, looking at the sampling of these distributions, the optimum sampling method, and trying to say, can we better represent some statistical properties of the underlying distributions of these parameters? And so we hypothesized that we could account for those in such a way that it would substantially influence the predicted coastal still water levels, which has the potential to ultimately alter coastal flood risk mapping results. And we specifically looked at higher moments than had been considered for the distributions of skewness and kurtosis, as well as for the storm heading, that landfall approach angle, the periodicity of that distribution. I have a all right, so moving into the methodology. So as we mentioned, we broken this up into 3 objectives. So good place to start is with the first one. So I'm actually kind of showing you a preview of 1 and 2 here. We're looking at just the rainfall model here in objective 1. In objective 2, we'll look at the rainfall runoff model and storm surge, but just so you can kind of see how that's going to be linked together in the future. So for the rainfall models, there were several parametric rainfall models that were developed beginning in 2003. There were 6 main models in the field that we found. I'll get into each of these that we used. Model code was not directly available for any of them. And so Dr. Kayanapu and I wrote a paper in which we wrote code for the 4 of these models. 2 of them were developed by proprietary purposes by insurance companies. And so you can imagine the publications for that did not include every step-by-step that you needed in order to get that working yourself. So we only considered 4 models here. First one of those is R-CLIPER, the Rainfall Climatology and Persistence Model. Essentially, it's a climatological mean rain rate. And the way that they parameterized the rain rates on these is just roughly an exponential decay function out to the edge of the storm. There's a little bit of accounting for the eye wall region there, but essentially it's just an exponential decay. The next model was the IPET model, the Interagency Performance Evaluation Task Force report. So that report was actually commissioned following Hurricane Katrina. As we talked about, Hurricane Katrina was largely a storm surge driven event. And so pages and pages and pages on storm surge, you have to go to the 8th sub-appendix of that report to find this rainfall model. In their words, it was not of primary concern. And so this is a relatively coarse model. Essentially, they recognized that for storms in the northern hemisphere that are propagating toward the north, they're spinning in such a way that the wind speed is actually added to the translation speed on the right-hand side of the storm and subtracted on the left-hand side. So storms tend to be stronger on the right-hand side. And they recognize that, but again, this was not their primary concern. So they said, okay, we're going to fit a curve fit very similar to what our CLIPER did, but on the right-hand side, we're just going to multiply it by 1.5. That's how they dealt with that. So another model came along and said, oh, well, maybe we can do better than our CLIPER, maybe we can do better than IPET. The parametric hurricane rainfall model, and said, well, all our CLIPER was missing was a few more factors. We just need to include wind shear and topographic effects. I'll save the meteorology lesson for today, but essentially 2 more factors that they were considering in that model. And finally, the last model that we considered in this was the PDF precipitation, climatology, and persistence. You're noticing that climatology and persistence in there a lot based on these mean rain rates. Essentially, what P-CLIPER did was look at historical data and scale our CLIPER in such a way that you can put a value for this variable f and set it from -90 all the way up to +90. So -90 is going to turn this exponential decay practically to 0, and so then you get hardly any rain. If you tune it all the way up to +90, so you have that kind of tuning knob, you're turning all the way to the right, you get more rain than we saw in Hurricane Harvey. So we looked at each of those models, and as far as the joint probability parameters, we kind of have that on the left-hand side of this table here. So these F, elevation, and shear were not joint probability method parameters, but the others were. So some people prefer the pictorial example. So let's go ahead and just show that real fast. So this is the very complex rain rate that you would look at from radar. This is Hurricane Francis in 2004. Just a single snapshot over an hour. Looking at one of these statistical models, let's take IPET as an example. You see this kind of averaging out over that entire area. So there's some area that didn't have rain in the real world that had rain in IPET, but there's large bands that are not captured at all by IPET. Similarly, we have that problem with P-CLIPER. So that's that F equals 30 kind of more middle of the road on that tuning knob. And then if you tune that all the way to the right, we have a lot more rain than actually occurred at that time. So let's move into objective 2. So as I mentioned, we'll be talking about the rainfall runoff model and then the storm surge model from that. So we'll begin with the rainfall runoff model. The model we chose for this was the gridded surface subsurface hydrologic analysis model. It is a diffusive wave hydrologic model. So that allows us to have unsteady specified head boundary conditions that vary with time. That is one of the big advantages of Geisha. One of the big drawbacks of Geisha is that it is a square grid of uniform resolution. And so if you want to cover a very large area in this, you either have to use a less representative grid or far more grid cells in order to accomplish the modeling task. So Geisha performs overland cell-to-cell routing in a 4-directional von Neumann neighborhood. It uses the Manning's equation for routing. I'll briefly show that there. And so essentially what it's doing is it is explicitly routing flow from the center cell to the right and from the center cell down and storing that in these variables QX and QY that are just flow rates. It keeps track of that and then updates the height in the neighbor cells based on the flow rates. So that was relatively quick and painless on the rainfall runoff model. Now we're going to get into the storm surge model. So the storm surge model that we chose for this is the advanced circulation model. It's called ADCIRC for short. And unlike Geisha, ADCIRC is a flexible resolution. We can have a finite element mesh with really fine resolution close to the coastline where we care, and really relaxed resolution out in open ocean to save on the compute cost on that. So we can have way out in the middle, near Bermuda, where we don't have a lot of resolution, but you get close to areas where you have a ship channel or something like that, you can refine this. People have refined it all the way down to 10 meters in some instances. So you can get down to the property level results with AdCirc. So kind of looking at some of those results, this is from Hurricane Florence in 2018 in North Carolina. So just kind of looking at the general state of North Carolina there, the maximum water height is what we're looking at here. And so you can kind of see that spread out throughout North Carolina, Pamlico Sound, and then you have the barrier island here, which is causing that discontinuity where this storm surge is piling up against the barrier island, and then you're not having as much generation. But over this area, you can generate more because there's enough time, enough distance for wind to generate that storm surge like we're talking about. And so we care about inundation over land. It was already ocean. It's not really our problem, right? So just scaling that down to look at just inundation, this is what we're most interested in for flood risk mapping purposes. It's also helpful if we can look at that over the course of time for evacuation purposes, for different things like that, for planning. And so these are also results that you can get out of AdCirc as well. With any model, there's a representation that has to be made somewhere. It has to be made so that a computer can understand it and be able to do computations with it. And so some sacrifices have to be made as far as what we're talking about. Even though we're able to get down to the 10-meter level, water doesn't move on the 10-meter scale necessarily. When you see the tide come in, it comes in very, very slowly, right? So you have this actual water's edge that can progress, but we're having to tell the model at certain places, there's water here, there's not. And so this is the wetting and drying algorithm in AdCirc. And so there's a lot of algorithmic rules as to how that all works. I won't bore you with the details on that other than this one specific rule that was written to say, if you tell it that there's water coming in via a specified discharge boundary that's actively discharging flow, it has to accept it. It has to stay wet so that it will perform those calculations. If it was dry, that mass would just disappear. So speaking of feeding in flow into this storm surge model, some of you can probably see where this is going already. We have the ability to do non-periodic normal flow boundary conditions in AdCirc, and it's just a flux per unit width. So it's a flow rate per width there that can be specified as either Dirichlet or Newman boundary conditions. So just as an example, we have an AdCirc mesh here now shown in a 3D view, and we have two nodes and a river that we're going to put a specified flow into, just based on this hydrograph. It's really probably not physical to have them different like that, but just for the sake of argument, let's consider that for the moment. And so let's say that leads to this water surface elevation here, where we're within the banks, and these two nodes are wet. This element is wet. These elements right here are partially wet. But if the flood rises in such a way where now the water surface elevation is here, we have these additional nodes that have to be wetted and these additional elements that should be wetted. And so knowing that ahead of time and having to specify a flux per unit width with something that can change with water level adds to a lot of really complex interactions that can occur there, as well as what we already talked about with dry elements, even with specified non-zero fluxes going into them, ultimately receive no flow in AdCirc. Alrighty. So I mentioned that some of you probably saw where we were going with that already with storm surge models, and then we're putting flow into it. We're getting flow out of the hydrology model. So let's talk briefly about how we can couple these models together. So there's four main types of coupling. One-way linking, where you're taking the results of a completed model and using it as boundary conditions for another. It's not really coupling per se. Then there's two-way loose coupling, where these models can exchange information iteratively as output files that are written to disk. So essentially, it's the standard output files that you would get from a model along the way, and they're being read in to the other model. And so that's got a lot of overhead as far as reading and writing to disk constantly. Two-way tight coupling, the models actually have direct access to each other's memory if you do that in an OpenMP or MPI framework. And then two-way full, where really it's not even coupling anymore, you've just combined everything into a single code at that point. So a lot of prior work, because it's easier to do, has provided one-way linking. So getting a hydrograph from Geisha and then putting it into AdCirc when you already have the whole hydrograph. And so you could do things like determine the active flow width and all of that ahead of time, or do completed storm surge results and do that as a Geisha boundary condition. However, we contend that two-way coupling is necessary for fully capturing the interactions between storm surge and rainfall runoff flooding, especially when you're not sure exactly where that boundary might be in any given situation. And then, of course, the difference between the two-way loose and two-way tight is just the medium of exchange, whether it's through output files or through direct access to memory. Of course, anytime we start talking about communication with computers, we want to know about the overhead. We want to know how often are they going to communicate? Is it going to be every single time step, or is it not? And so a decision that has to be made is the coupling time step, the interval at which these coupled models exchange information. So smaller coupling time steps, as I just mentioned, will incur more communication overhead. You're spending more time just having the models talk to each other than you are having the models actually solve anything. Two-way tight coupling is probably kind of the best world as far as that, because it reduces that overhead. You're not talking through writing out to disk. You're now talking through direct memory. But then on the other side, with larger coupling time steps, the model solutions can potentially diverge very far from each other. So if you don't set that at an appropriate time, you have these two competing things, either one of which can bite you. So looking at the coupling time steps that were selected in this study, so we had the rainfall model that's providing rainfall rates. It could be at whatever time step it wants to be because it's just a rainfall rate, so you're just integrating over time. 15 minutes, we're providing that to Geisha. And then Geisha and AdCirc exchange information every 15 minutes. So Geisha is sending discharge into AdCirc, that inflow that we're talking about, and AdCirc is sending a water level back to Geisha. Sometimes, under conditions that I'll elaborate at a little bit, Geisha will also have an opportunity to send a water level back to AdCirc, but primarily AdCirc is sending a water level to Geisha. So as we talked about, AdCirc and Geisha simulating different physical processes. So AdCirc was designed to simulate wind-driven storm surge. So there's no precipitation methods available in it. Geisha, on the other hand, was designed for precipitation-driven overland flow. So no wind-driven flow methods available. So wherever one model's domain stops, we lose the picture of the involved physical processes. So if we want to couple these models together and get the biggest bang for our buck, we want to say, where are the regions where wind-driven or precipitation-driven flooding dominates? If we try to physically overlap these models so that we can try to simulate both at the same time, it leads to problems with continuity of the water level if your coupling time steps aren't every single model time step, at which point you might as well write a full code and not try to couple these models together in the first place. So our solution to consider the areas where wind-driven and precipitation-driven flooding dominates is to require a single curvilinear interface between mutually exclusive models along some boundary line. We say with some boundary line, well, where are you going to put that line, right? Because there's different areas where that could be important. Some things that sprung to mind were the 0-meter elevation contour. Well, if you do that, you can't simulate storm surge beyond the beachfront, which is the whole point of these tropical cyclones. With storm surge, it's usually going to expand beyond the beachfront. The 10-meter elevation contour is kind of the reverse way of looking at that. Say, okay, well, we can simulate storm surge up really far as we possibly would ever expect it to go, and maybe even further than that. But then you lose the ability to simulate rainfall runoff in that area. And that is a large amount of area to sacrifice in these low gradient coastal areas. And then, of course, you have the X meter elevation contour. Somebody says, oh, well, let's do 5 or let's do 8. Try to come up with some compromise between these two. But it is just that, at the end of the day, a compromise is going to lose out on one of these. And so we need a physical representation of the region where storm surge processes dominate specifically. So in order to develop a methodology to figure that out, we looked at the case study from the Tar Pamlico and Neuse River watersheds in North Carolina. There was a study done by the North Carolina Floodplain Mapping Program in 2011. It was a JPMOS study with those 5 parameters: the intensity, storm size, forward speed, heading, and then one that we haven't talked about so far is wind field structure. We're not going to dwell on that today, but 5 parameters just the same. Give you a sense of the scale of the amount of results. 2.5 terabytes of results in this, and that's really just the maximums, not even a lot of time history of the full global area. And that was generated from 675 synthetic tropical cyclones. So the realizations of the joint probability method, the particular cases that were considered. So there were 324 landfalling storms that followed tracks similar to this in North Carolina, 324 bypassing storms, and then 27 storms, these are relatively rare, where the storm stalls out and then landfalls a little later after weakening. So back to how can we use this information to get a physical representation of the region where storm surge processes dominate? Well, we said, okay, we're modeling storm surge in AdCirc. We're not modeling rainfall runoff, just storm surge. So let's take the results from that and contour the line of AdCirc nodes that are inundated in only one out of those 675 storms. If it was inundated in more than that, we didn't want the line there. We wanted it at the most extreme boundary that we would see with those storm surge results. So this represents the maximum expected influence of storm surge, kind of following a line kind of like this. You notice it's pretty close to the coastline, but it does actually move inland a little bit. So there is some storm surge penetration that is occurring there. And so as a result, this does no longer correspond to a single elevation contour. It goes all the way down to half a meter below NAVD 88 and almost 16 meters above in a few cases. But on average, it's about 3.5 meters above. So now that we have the line of where we want to couple these models together at, we have to look at the mechanisms that we would actually use for that. So there's been a prior point-to-line coupling that has been done of Geisha and AdCirc. Dr. Gajanan Chowdhury at University of Texas A&M put together Python wrappers of AdCirc, Geisha, and then a coupling framework in order to do point-to-line coupling. Well, that's appropriate for a single riverine coupling boundary about 100 meters wide, where you're considering a single point, as in the case here. So we have this watershed that's draining. This is the Geisha model, AdCirc model. So we have Geisha point-to-line. So we have a single point that is then feeding information to all of these points in AdCirc. And conversely, all of these points in AdCirc are actually having to get averaged to feed a single value back into Geisha. So you can see how that works well for a very small coupling boundary, but for one that's 1,000 kilometers long, like we're looking at, we need a more physically realistic approach. We need what I call line-to-line coupling, which is now where we have coincident cells and nodes in AdCirc, we are directly connecting them to each other. And so there's a lot more connections that have to be made between Geisha and AdCirc. So another reason to go to line-to-line coupling is that point-to-line coupling, based on the way that a watershed is defined as the area that drains to a particular point, you pick your point, you have a certain area that drains to it. If you want to consider other area, you're going to have to pick a different point. If you have to place that point above storm surge, as prior work did because they used kinematic wave solvers that couldn't accept storm surge boundary conditions, then you have to place that well landward of any storm surge effects. And so in previous studies, they simulated this area up here in red for hydrology and this area down here in blue for storm surge, but because of the way their watersheds are defined, they actually couldn't simulate this area here in purple at all. So a line-to-line coupling approach allows us to move that model boundary way down here, where now we're simulating the area that is important for storm surge, but we're not losing this area here for hydrology. We're able to now simulate that. So we get a better accounting for the volume of rainfall runoff than prior work. So now kind of moving into the third objective on the methodology. So kind of shifting gears, we're not going to talk about computational models for a second. Now we're going to talk more about the joint probability method that we were looking at. So when we're using those joint probability method or optimal sampling approaches, typically what's done is appropriate statistical distributions are fit based on historical data for each of those parameters that we're looking at. Well, as we talked about before, we have limited compute power. We can't simulate this entire distribution or even a very fine-grained representation of that. So we actually discretize it into specific cases for simulation. So a handful of point masses, 2, 3, 4, maybe 5 point masses if we really have a lot of compute power to throw at things. So this is just an example of central pressure depression there. So farther you go to the right, the more severe the storm is there. So kind of more middle of the road storms. This is from the 2011 study. That 2011 study, we looked at expanding that with potential improvements on the fitting of these distributions and the discretization processes in order to explicitly consider higher moments than have ordinarily been considered. So usually mean and variance are matched. We want to look at skewness and kurtosis as well. For those of you who it's been 10 years or more since you've had statistics, briefly, skewness. So essentially, it's the direction that the long tail of the distribution is headed in. And the more severe that tail is, the more skewed the distribution is. If it were perfectly symmetric about a single vertical line, then it would have zero skew. We also wanted to consider, as I mentioned briefly earlier, the storm heading angle for those circular data, recognizing that angles are on a circle, essentially. A lot of times distributions are fit to them in a linear fashion, not recognizing that 360 degrees and 0 degrees are the same. The difference between 359 degrees and 1 degree is only 2 degrees, not 358, right? And so we wanted to consider that as well with distributions that completely wrapped around a circle. If you prefer seeing your distributions unwrapped, this is what that distribution looks like unwrapped. But this is just a von Mises circular distribution that was fit there. We also were able to incorporate new storm data. Since it's not 2011 anymore, we have a longer period of record, 1940 to 2018, that was available when we did this study. And then there were also weaker storms that were neglected. So the storm surge was the only thing that was being modeled. Rainfall runoff was not. So they recognized that storm surge is driven primarily by wind and said, okay, let's only look at Category 2 hurricanes and above. That was where they drew the line. And so they fit statistical models that were appropriate for that so they could fill in data there. But they did not include weaker storms. However, as we've noticed with Tropical Storm Faye, for instance, you can have the 100-year total water level from just rainfall runoff, essentially, and very little from storm surge. So we now have to include those weaker storms as well. And so that means that, unfortunately, we weren't able to expand this to a couple of their parameters because their statistical models had to be expanded. And so we could expand that in the future, but we did not in this study. Briefly, just the distributions that we were looking at, looked at a uniform, normal, log normal, exponential. I'm just kind of go through these and point out the key ones. Weibull distribution was one that was important as well, typically used for modeling extremes, and Gumbel and Gamma as well. And then we also looked at the logistic family, although I don't believe we actually used any of those at the end of the day. The circular distributions that we considered were the wrapped Cauchy, wrapped normal, von Mises, and then a circular uniform distribution as well. So in order to fit those distributions to the data that we had for each parameter, we used maximum likelihood estimation, as well as the AICC. So that's the AIC with the small sample size correction to select which models were appropriate for use, had the fewest parameters, but still had did a good job accounting for the likelihood that the data were actually drawn from that distribution. So once we selected each distribution, we then wanted to double check, because AICC is just a relative measure. If we had chosen a different distribution, a different set of distributions rather, we might have gotten a different answer. AICC is only relative, so we wanted to look at absolute goodness of fit in the Anderson-Darling goodness of fit statistics. So we computed that to test against the null hypothesis that the data are drawn from the distribution, and then rejected that hypothesis if the test statistic was significant. Unfortunately, you can't use Anderson-Darling for circular distributions because it is not invariant under a rotation. And so you have to use the Watson goodness of fit statistic for circular distributions. All right. Like he's 40 minutes in, we haven't got to the results yet. So we're going to move into those right now. So looking at objective one. So very, very briefly, if you were here for my proposal, then you've seen these results already. The paper that Dr. Kaganapu and I published in the Journal of Hydrology finally made it in 2020. And so looking very briefly at the rainfall simulation that was done, we did that on a evenly spaced 0.1 degree latitude longitude grid. So just to give you an idea of how dense that is over North Carolina. And then also looking at, well, what if we looked at the centroids of small coastal watersheds that are in that area as well? And so then we simulated on both of them and looked at the equitable threat score skill metric. So a higher equitable threat score, we're doing a better job of capturing the important events there. Looking at the IPET model that you see in this purple line here, notice these are at rainfall thresholds. That's a logarithmic scale there. So at 100 millimeters, you're at about 4 inches. So you're starting to get to the amounts that we care about for tropical cyclones. Obviously, you're at 40 inches up here. And so unless you have an event like a Harvey, you're really not simulating that at all. Not that any of these models really gets to that point. But IPET is really the one that's looking the best for equitable threat score in the regions that we care about as engineers. And then when you average that over the small coastal watersheds that we're really wanting to look at, it tends to increase all of the equitable threat scores, but then that picture is even more complete with IPET still shining through at the highest levels that we care about. So that was all on Objective 1 because we've beat that to death in the past. So the new results that we're talking about today are in Objectives 2 and 3. So for Objective 2, we were looking at that coupling boundary of where are we going to place the line between Geisha and AdCirc, and we had that trade-off between simulating areas for hydrology and simulating it for storm surge. So one of the state-of-the-art systems was ASGS Storm, and that was actually a point-to-line one-way coupling system. So they had that in there. They were using HL-RDHM, which is just a different hydrologic model that we didn't use at all. So that's what's going on there, if you see that. So they simulated about 58% of the area for hydrology and about 30% for storm surge. But as we mentioned, they had a decent area that was not considered at all, almost more than 10% of that. The 2011 study didn't include hydrologic effects at all. And then if you were to pick different contours, as I was talking about kind of choosing that X meter contour, we can look at the trade-off of how that ends up being. So obviously you choose the shoreline for areas above the shoreline. It's 100% of the area that you'd be simulating for hydrology. You're not doing storm surge at all at that point. That's the coastline coupling scenario. 5 meters, as we kind of talked about a little bit, you're now at 87% of that for hydrology, 12% for storm surge. And the trend continues all the way up to, you're doing 32%. So you're basically in the same place at the 15-meter contour that they were, even though they weren't using the 15-meter contour explicitly. However, with our new coupling boundary that we've chosen, based on looking at the maximum expected influence of storm surge, we're only simulating 6.5% of the area for storm surge, but that's the area where storm surge is important. The area where hydrology is now probably the more important of the two, we're being simulated over the rest of the area. In order to do all of the coupling that we had to do, we had to keep track of volumes that were being sent over particular times. And as anyone who's done computer modeling knows, that's a headache in keeping track of and integrations and all of that. So we had to add some new variables into the Geisha source code to allow it to keep track of the volumes that cross these cell faces. So for routing QX, like we talked about previously, we have this face volume that's just adding up how much water has crossed over this face in a particular time, positive if it's going to the right, negative if it's going to the left. So we have 4 variables that had to get added to that. And then anytime you add variables to somebody else's code, you need to make sure that it works. And so we tested it in 4 different scenarios for its mass conservation properties to make sure that it was indeed conserving mass as it was. You look at these percentages and you go, why did he show this as percentages and not in scientific notation? That tells you we were within the rounding error of even what Geisha will report to us for the volumes. So we're confident that that is, in fact, conserving mass as designed. Then also looking at the infrastructure that is needed for this 2-way tight coupling. Essentially, it's 2 one-way coupling operations that are performed in a specific sequence. AdCirc driving Geisha, so passing storm surge into Geisha, and then Geisha driving AdCirc, so passing discharge from Geisha back to AdCirc. And so that coupling, we wanted a system that relies on the model's geographical intersection. So you notice that we have this geisha model in blue up here, and this model in red that is AdCert. So they're overlapping in this area. And so we say, wait a minute, I thought we said we had to have mutually exclusive domains. What do we do there? We have to give one of them priority. And so because storm surge generation is something that we expect to be more important in the area that we've given to AdCert, we let AdCert have priority in those areas. So then forcing geisha with AdCert values is relatively straightforward. Based on continuity, the water surface elevation has to be the same in areas that are physically coincident. And so we looked at the maximum influence of storm surge and had to do a transition zone width because of mismatch resolutions, things that we don't have time for today. But that single curvilinear coupling boundary that we had, and that area was where we assumed that storm surge was dominant. And so we allowed AdCert to override geisha in that area, as I just mentioned. In the other direction, however, it's a lot more complicated. Forcing AdCert with geisha hydrographs, we already had to add these new variables just in order to properly conserve mass. So we account for the flow volumes that are being routed across cells and then from geisha cells into AdCert as well, by comparing these cell sums of phase fall variables at the beginning and ending of coupling time steps, getting the difference in volume there, and then dividing that by the time it took to get a flow rate, and then further dividing that by the length of the line of AdCert within the geisha cell that flow is being received over. So it's that nodal flux per unit width that AdCert is expecting to get. It's not the whole story on this equation. We're going to come back to that actually right now. So those phase fall values are actually calculated assuming that all of these geisha cell faces are available for flow. Because geisha doesn't know what's being run in a coupled sense. There's a Python script up above that knows that they're being coupled, but geisha doesn't actually know that. And so only part of a cell face may be available. If we have a mutually exclusive domain of AdCert, this part of the geisha face is not available for flow, and vice versa. We have this area that's not available, but this area is. So those pink arrows are showing the areas that are available for flow. You know, some are 0%, some are 100% open, some are 50% open. And so we have this new variables that we've had to introduce at the Python water coupler level to keep track of how much flow is actually going across with geisha. And so it's just a decimal between 0 and 1. If you look at cell 14, for example, from above, this whole face is available for flow, and so it's 1. If you look at the left, well, AdCert's actually got that whole area. You look at below, AdCert's got that area too, so those are both 0. And then if you look at the right, only half of it is available. So essentially what we did is then just took those proportions that are available for flow and multiplied it by the flow in order to get the correct volumes that would be then going into AdCert. Again, we had the issue with AdCert regarding wetting and drying that we talked about, that even though the comments in AdCert specifically state that specified discharge boundaries require elements to stay wet, we didn't find source code implementation of that, and experiment also showed that with the AdCert code that this rule was not implemented. So these dry AdCert elements, even with specified non-zero nodal fluxes, ultimately will simulate no flow in AdCert unless we do something about it, resulting in a loss of mass, which should be entering the AdCert domain. So in order to overcome that, we had to employ additional logic at the water coupler level. We went for a two-pronged approach, essentially saying, remember that if AdCert is wet, we have that storm surge that's coming in that we presume is dominating. So we want to leave wet AdCert nodes alone. So the first thing that we said was, we're going to make sure that it's dry first, because that's the problem we're trying to avoid, is if an AdCert node is dry. Then we also wanted to check if the geisha water surface elevation, so where this water surface is here and versus this water surface in AdCert, if we copy that over like this, so kind of toggling that back and forth so you can see that, would it be high enough that AdCert would now see this element as wet? And so we looked at both of those conditions and said, if both of those are met, then go ahead and override the AdCert water surface elevation, in this case, with the geisha water surface elevation. So remember when I said sometimes geisha can put a water level into AdCert, this is the only case in which it can do that. Now moving into the objective 3 results. So looking at the impact of skewness on coastal still water levels, and we had a reviewer comment that said, why does skewness matter? You know, is it just does it have an impact on the coastal still water level, essentially? And so we did a brief sensitivity experiment where we looked at if we have skewness represented versus if we don't have skewness, we have symmetric distributions, or we have what was done previously. What is the differences in coastal still water levels that we would see there? So we looked at 3 different sites, looked at an open coastline, looked at a back bay, barrier island. So this is behind the barrier island. Remember that discontinuity that we showed in the maps previously, and then a riverine USGS station. So where storm surge is largest, we have the largest potential differences. We have almost a full meter of potential play in that, depending on the skewness and weighting scenarios that are used there for this open coastline. That effect gets smaller as storm surge itself gets smaller, but it's still not something that we should probably neglect. We should include skewness based on this sensitivity experiment. So then we did. We went ahead and fit those distributions that we talked about, the 4 or 5 slides of distributions. We looked at all of those and said, okay, run AICC, run Anderson-Darling, and which distributions are the best to use. So we fit for central pressure depression. I'm not going to show you all of these. I'm just going to show you one of them. Central pressure depression for the landfalling storms. We had 30 storms. Uniform distribution. Anderson-Darling says no, absolutely not. It has 2 parameters to it, so that's why the AICC is so low. For a Weibel, again, 2 parameters that we're fitting there, but it's more of this skewed shape, and so it's able to capture that better. Anderson-Darling says yes, it is likely that the data could have been drawn from this distribution. It's not unlikely, is what it's saying. And so every time you flip stuff around like that in statistics, people get all antsy about that. So just saying, it's not unlikely that it was drawn from that distribution. Double negatives are always fun. So the bypassing storms that we looked at also fit an exponential and a Weibel as well. And the exponential actually comes out as the first fit that we wanted to look at there. You notice that we have these other storms, or not other storms, other distributions, excuse me, that are beneath this, and we have this thing called AICC evidence ratio. Since AICC is a relative metric, if it's just 1,000th of a point better, then you would select the other model. Well, really, if that model weren't in consideration, you would have selected the one just beneath it. And so we want to say, how much better is the model that you chose versus the one that you didn't? What is the ratio of evidence that would be the adequate model to look at? And so here, the Weibel is 2.68 times more likely to have been the best fit model that we could get out of the candidates we had. And the exponential is 1.6 times more likely than the Weibel to be. So remember, once we had these distributions, we then had to discretize them into point masses. So this is what the 2011 study did for central pressure depression, same variable we were just talking about. And so we had those exponential and Weibel fits that we just talked about. So I'm going to throw all of that up there at once. So we now have 2 different distributions down here for bypassing and landfalling storms. And we have additional point masses for these bypassing and landfalling storms. And yes, this green is the full height that's not stacked on top of there. It's just at the same place. Also, we wanted to look at the same process for the circular distributions. Essentially, it's the same idea as before. We found that a von Mises fit was more appropriate for landfalling headings and RAP normal for bypassing. And the AICC evidence ratios are way out of the park this time. But if you look at the AICC differences, I don't think anybody's going to choose a circular uniform model over the von Mises looking at AICCs that are that far apart. So looking at the landfalling and bypassing headings that we had, this is the data that we had, and then the fits as far as the discretizations that we looked at. So looking at landfalling storms that were landfalling at each of those angles and bypassing storms, bypassing at each of those angles. So then we also wanted to look at, can we actually represent skewness with these distributions? Because if we end up fitting a bunch of symmetric distributions, then skewness really isn't a concern for symmetric distributions because it's automatically 0. in a symmetric distribution. So we looked at wind speed, central pressure depression, translation speed, heading, and found the first thing we looked at was the data skewness itself. Is there skewness in the data? Because if there's not, we don't need to be trying to represent it in our distributions. And so for wind speed, we actually didn't find statistically significant skewness there because that overlaps 0. And so with the data that we have, bootstrap sampling it, we're really not sure that it's not 0. However, we had for central pressure depression on the bypassing, and then both translation speeds, landfalling and bypassing, that confidence interval does not include 0. And so there is statistically significant skewness that we can detect with the data that we have. And so we said, okay, well, we need to include that skewness as best we can. What about the distributions that we looked at? Do those account for that? And so these are the fits that we ended up with. Some of these distributions have specific skewness values that will always be the same no matter what. And so that's an additional thing that can be looked at in future work as well. But then with the heading as well, had to use circular skewness, which I had to go and pull a 1972 book out of the library to discover how to do that. That's not a fun thing to deal with. I don't recommend it. So anyway, so looking at the conclusions, tying it all together. So objective 1, we had these statistical precipitation models from running off of just a handful of parameters. So evaluated over the 2004 to 2017 Atlantic tropical cyclones, the IPET model currently demonstrates the highest skill of the 4 that we looked at. However, we caution people that none of those statistical models presented in this study perform as well as the dynamical models of even 2007. This level of performance is expected since those models were developed using training data from 1998 to 2002 and then evaluated over the period 1998 to 2004. My machine learning friends are groaning back there. You're using your training data as testing data. And so when we put in unseen data 2004 to 2017, of course, it's going to perform worse. And we would expect that performance to continue to degrade as climate change progresses and the climatological mean rain rates change. So none of those models is recommended for direct use in coastal flood studies, but the model selection criteria that we looked at is recommended for use in future studies. Looking at line-to-line two-way coupling, the case study from North Carolina was undertaken to develop a methodology for determining that location of that coupling boundary between AdCirc and Geisha. We placed it at the local maximum expected influence of storm surge. Between that placement and the flexibility afforded by line-to-line coupling allows for the simulation of hydrologic effects in 46% more area than the state-of-the-art system that used point-to-line one-way coupling, so we can better account for the total volume of rainfall runoff flooding. We also developed an algorithm to simplify the two-way coupling of an arbitrary pair of AdCirc and Geisha models, gave AdCirc priority because we assumed that storm surge was going to be more important where AdCirc was. And then the line-to-line coupling case study in North Carolina and then the theoretical development in this study provide a springboard for future work to fully implement that two-way coupled simulations of combined storm surge and rainfall runoff flooding scenarios. And then for objective 3, we tested several potential distributions to update the JPM-OS storm surge parameters. We found statistically significant skewness in the variables of central pressure depression and storm translation speed, indicating that we need to fit distributions that can represent this skewness. The best fit distributions largely consisted then of the Weibull and Gamma families and were used for further analysis. We broke those into 2- and 3-point approximation methods to discretize those into the point probability masses in preparation for a future JPM-OS analysis. We would want to include 4-point, 5-point methods as well. Unfortunately, we were not able to get to that in this study, but that is something we want to look at in future work. And then while storm size was not considered due to the shorter period of record, we're looking at future work to extend the database backwards so that we can include storm size as well. So overall, we had objective 1, these statistical tropical cyclone precipitation models taking very limited information and providing us an average picture of the rainfall that we would expect. We're then able to feed that into objective 2, the line-to-line two-way tight coupling with a hydrologic model, so then we can look at the rainfall runoff from that and simulate the storm surge as we were before. But now they can talk to each other and influence each other where we have these nonlinear interactions as we have observed historically. And then we also considered updating the JPM-OS distributions so that when all of the model computations are done, for sense of scale, about $100,000 worth of compute time, about a month on a supercomputer with 1,000 nodes on it. So we want to make sure that when we run this, we don't have to run it again. So we want to make sure that we're running this for the right distributions and the right point masses. So overall, taking these together will result in improved modeling of nonlinear interactions of tropical cyclone storm surge and rainfall runoff flooding. So I would like to acknowledge the Water Center for funding the first few years of this work. And then, as Dr. K mentioned, the NSF Graduate Research Fellowship Program as well, both of which, without whom this work would not have been possible. I'd like to thank all of you for coming here today. Dr. K, of course, thank you for all your guidance and friendship over these years. The committee, friends and family that are here today or joining us virtually, thank you so much for being here and for all your love and support over the years. So that I have way more slides of references than I probably should. And with that, I will take questions.
Questions from general audience, please. And if there are questions from online audience, feel free to put them in the chat and we can open up from here.
The nonlinear aspects versus linear.
Oh, goodness. Yeah, I mean that very differently than the structural sense, don't I? Oh. So the question was about nonlinear versus linear interactions. Do you have a specific question on that, or
just what's nonlinear about what you're doing?
Yeah. So the nonlinear part of it, because Nick asked, what is nonlinear about this? Linear interactions, to me, is superposition of storm surge and hydrologic effects. If you just add them together, you run the model, they don't affect each other at all, and you just add them on top of each other. Well, of course, you're going to get a way bigger flood than is ever actually going to occur, because that's not what happens in reality. But you can't consider either one in isolation either. And so that is the nonlinearity, as it were, in this case, allowing those two to interact with each other and not just superimpose them on top of each other. Yes, George. Man, I've been dreading getting questions from all day.
Good job. I think you need a whole team to break down your presentation.
Anyway, this has been cut for time.
Yeah. The question I had was.
Okay. 87. Missing that. Yep. Okay. Yes.
Yes. Okay. So this is where you talk about the two models. Right?
Correct.
You said ADSEC is more flexible than Geisha.
Mm-hmm.
First of all, in what sense is it flexible? Can you adjust the edges of the ADSEC model?
Yes.
Okay, so I can see that in the subsequent slides, you erase some of the edges of the Geisha model. That's fine. Just if you can, just so that you can, yeah.
Oh, yeah.
Exactly. Couldn't you have molded, I'm using this term, like not in a technical form, but couldn't you have molded the ADSEC edges to fit into the Geisha boundaries?
You could. So the question from George is, could you more carefully design the ADSEC model and make the mesh exactly match Geisha boundaries, right?
Yes.
So yes, you could, if you didn't already have an ADSEC mesh that was built. We were trying to reuse a mesh that hundreds of man hours went into building to be able to reuse that mesh. So that was something that was not considered in this. We actually, ironically enough, cut for time. We looked at matching the resolution and trying to say, can you have that where it exactly matches? And we actually did do that. We just didn't have time to show it today. As you saw, we already ran probably a minute over the allotted time that we had planned there. So yes, we did think of that. We do have that. If you'd like to read the dissertation itself, we discussed that at great length. Well, you don't have to read the whole thing. Maybe 10 pages out of it, but still.
When you did that, any beneficial than
What do you mean?
Like, all the issues that I know you presented, you had to tackle, wet, whatever.
Yeah. So the
Did it make the whole problem simpler when you molded it that way?
yes. So the question was, did our choice of coupling boundary and coupling style make it easier, even with the resolution issues, right? We looked at it with the resolution matching. So we had an algorithm that we looked at for ensuring that there was a transition zone between AdCirc resolution and Geisha resolution. Having those exactly match the cell centers does simplify a lot of things. It may not be the most physically representative thing. Unfortunately, we don't have as many model results as we would like to be able to show you at this point, because it's just something that's going to have to be done in future work. So that would kind of tell you from a more practical standpoint, but from the theoretical standpoint, we considered that, and it does simplify a lot of things. But you could, in theory, have an arbitrary AdCirc mesh there. And most of this works. You would just have to make a few fine-tuning adjustments in that case.
Thank you.
Uh-huh.
Thank you also. I mean, I've fed off the crumbs that fell off your dissertation and work. I mean,
Hopefully not literal crumbs. For those of you who don't know, he sits next to me and I eat chips a lot while I work. So.
The statistical analysis that you did, it really helped me. Paper review that I was
Sure.
doing.
Sure.
Thank you.
Glad to be of service. Any other questions? Yes, Collins, the other man I'm dreading questions from today.
I have two questions.
Okay.
The first one is on the solutions you do on objective one, that none of the parametric precipitation models are suitable for this coupled
Sure.
So you build this coupled model. So what type of precipitation sources do you intend to?
Yes. That was one of those things when we had the snafu, I was trying to cut things for time, as it were. And so there was a point that I was supposed to mention there. So thank you for reminding about that. Recent literature looked at our paper and said, oh, none of those work? Okay, we'll find a different one. And they found a different one. And they've got a system where they're doing coupling with HMS, RAS, and AdCirc. So a different way than we're doing it. They're not doing two-way coupling, but they're looking at a lot of other things. And in order to force that, they have a different rainfall model that's more complex, but can still use just the JPM parameters to do rainfall. So that has been tackled by research in the area, but not research that I did. I led to that by saying, hey, don't use any of these. And they said, okay, well, we'll find a different one. They found a different one, and theirs worked. So not all results could be positive, unfortunately, right?
The second question is, on slide 60, you mentioned that the ASEC is mainly driven by wind forces.
Yes.
Yes. So I know based on the percentage that falls within the Geisha area is that small in terms of percentage.
Yeah.
But if let's say we have an event and there's still rainfall activity within the portions that fall within the Geisha, the AdCirc domain, how uncertain, like what is the uncertainty? How does it affect your model?
So that rain is still going to be lost in this system, right? We originally looked at, okay, can we combine AdCirc where you have an ability to just rain on the grid, and then you don't have to do any of this, right? You don't have to do models at all. There's a discontinuous Galerkin shallow water equation model, DG SWIM, that is a cousin of AdCirc, but it is nowhere near as well maintained. The source code was a lot harder for us to access and to be able to use. So we considered that it's something that really the result here is more of the algorithm. I wish I had more results that I could show you and say, oh, well, it doesn't matter as much. But that is something for future work to consider, absolutely.
I read a paper by Bisky Italy. One that they mentioned there's a rain on grid or a rain on mesh model within AdCirc. I don't know whether you came across it.
No, we hadn't. That's probably DG SWIM. That, to my understanding. I'd like a copy of that paper if you don't mind, but. Any other questions?
Questions from general audience?
Anything online? Somebody's typing, oh boy.
Messages from Mackenzie. Great job, John. Message from Elizabeth Brackins. Great job. Great presentation, John. Thanks for sharing.
Okay. All right.
All right. In that case, thank you so much, audience, for taking time to come. Once again, let's give it one.